By now, you probably have been wondering just exactly what light is. You're not alone. At first, we were happy that Young's double-slit interference and then the diffraction and the polarization of light showed us how well light wave theory worked. Then we got blackbody radiation, photoelectric effect, Compton scattering, and pair production to show us how well particle theory of light worked. So is light a wave or a beam of particles? It seems that light must be more complex than just a wave or just a beam of particles. This is called the wave-particle duality. Then in 1923, French physicist Louis de Broglie suggested in his PhD dissertation that this wave-particle duality of radiation may be extended to particles such as electrons, protons, etc. According to the special theory of relativity, a photon has momentum p that equals to the photon energy E divided by the speed of light in vacuum c, which also equals to the Planck's constant h divided by the wavelength lambda. So de Broglie proposed that a particle with momentum p is associated with or guided by a wave of wavelength lambda that equals to h over momentum p, which is h over mv. And this wavelength is now called the Broglie wavelength. But at that time, his thesis committee members were not sure if de Broglie's hypothesis was worthy of a PhD degree. So they sent his thesis to Einstein to look over. Since Einstein endorsed the work, de Broglie got his PhD in 1924, and then 5 years later, a Nobel Prize for basically the same work in his PhD thesis. It may look like all de Broglie did was to rearrange an old equation to get a PhD and a Nobel Prize, but de Broglie's hypothesis on the wave nature of matter served as the basis of a completely new field of physics that transformed our understanding of physical phenomena on the atomic scale. Einstein said that de Broglie lifted a corner of the Great Veil. Of course, de Broglie's idea of particle wave or matter wave seems crazy because we don't see everyday objects acting like waves. For example, we can throw baseballs toward a small gap, but we don't see those balls diffract through the gap to form any diffraction pattern on the other side. Why is that? Let's try this calculation. A 0.145 kilogram baseball travels at 20 meters per second. Find the wavelength of this baseball. The wavelength is h over momentum, which is h over mv. Because everything we plug in is going to be in standard unit, so I need to use the h that is in the standard unit, that is the joule second, 6.63 times 10 to the negative 34th. And then divided by the mass, 0.145 times the speed, 20, and this will give me 2.29 times 10 to the negative 34th meter. That's a very small wavelength. If you remember, in order for the effect of interference or diffraction to be observable, the slit distance or the slit size have to be around the size of the wavelength. This baseball's wavelength is much, much smaller than 10 to the negative 15th meter, the size of a nucleus. So we don't have anything that is close to 10 to the negative 34th meters in size to show the interference or diffraction of the baseball. However, if we look at an electron, an object with a much, much smaller mass than a baseball, the wavelength may get long enough for us to observe its wave behavior. We will continue this part in our next lesson.